Welcome back. After having seen the operation of the diesel engine system in detail, we are ready to examine the various strategies implemented by the manufacturers in order to interact with the various elements present in the system and thus control the performance generated. Let's start with the primordial strategy called the mass flow metering, more commonly abbreviated as MFM. This strategy involves the use of some very important sensors, such as the mass airflow sensor, the manifold air temperature sensor, the atmospheric pressure sensor, and some specific maps present in the original file, to be able to determine the instantaneous airflow entering the engine and continuously check the carburation in an optimal manner. Let's dig deeper into this very simple strategy and see how to apply the formulas used by the ECU to control the main parameters and thus understand which maps to modify to increase performance on this type of system. Everything starts from the flow of air entering the intake duct, which is measured by the MAF sensor, which subsequently sends the signal to the engine control unit. The ECU, thanks to the values coming from the mass airflow sensor and various maps that indicate or predict the measured values, is able to control the correct operation of the engine. What does the mass airflow sensor measure? The mass airflow sensor accurately measures the mass of air flowing into the engine, so it is mainly used to calculate the amount of fuel to be injected and thus determine the correct air-to-fuel ratio. In diesel engines, thanks to this sensor, it is also possible to control the recirculation of exhaust gases and thus manage the opening or closing of the EGR valve. Be very careful. A faulty or damaged air mass sensor can transmit incorrect input signals to the engine control unit, which consequently incorrectly drives other components. If the stress on the air mass sensor is high, it can cause irreparable damage shortly after purchasing a new vehicle, especially in turbo diesel engines. How does the mass airflow sensor work? The complete air mass sensor consists of a plastic tube that sucks in air from the outside and passes it over a sensor positioned inside to take the measurement. Depending on the application and vehicle, the air mass sensor can be a single plug-in module or fully integrated in a plastic tube. However, both versions, with or without a tube, are called air mass sensors. Older models have a hot wire sensor, where any contamination on the wire used for measurement is burned off, and continue to be powered even after turning off the engine. Newer models, on the other hand, work with a film-like heating resistor placed on a support, without any self-cleaning function. This hot film sensor is heated to a constant temperature of approximately 120 to 180 degrees Celsius over the intake air, which cools the hot film sensor during its entry. The control electronics counterbalance the cooling by means of a heating current, which corresponds to the measurement of the incoming air mass. This method also takes into account the density of the incoming air. Therefore, the signal sent to the ECU is more precise compared to the classic method. It is very important to keep in mind that there are various problems related to this type of sensor. There may be errors in case of physical damage, such as presence of dirt in the airflow, which could damage the sensor, oil seeps from the crankcase, which could dirty the sensor, use of a poor air filter, water in the suction system. Other conditions may lead to an incorrect measurement taken by the sensor, such as a malfunctioning EGR valve, a faulty steam recirculation valve, loss of pressure in the intake system, a dirty air filter, damaged turbocharger or uncalibrated management inside the ECU. Problems like the one just seen could lead to specific direct DTC errors, such as malfunction in the air mass or airflow meter circuit, problem with measuring range or power of the air mass or airflow meter circuit, air mass or airflow meter circuit too small, air mass or airflow meter circuit too large, or indirect errors, such as insufficient flow rate, excessive flow rate, In the event that something does not work properly, the ECU contains maps called air quantity, which express, according to the engine speed and the fuel to be injected, the theoretical air mass value in input for each cylinder. Let's see how it works by giving an example. Let's say we are at 3,612 RPMs and we require about 33 milligrams of fuel for each cycle. The ECU, thanks to these values, is able to interpret the amount of air entering the engine, even if it does not have a measurement performed directly by the MAF sensor, so it can calculate the best air-to-fuel ratio to keep our engine constantly working in excess of air, since the instant air-fuel ratio corresponds to the ratio between the mass of air entering the engine and the mass of fuel injected. Applying the formula to our example, we find that the instant air-fuel ratio is equal to 25.75. As we know from our previous meetings, this value corresponds to a very lean carburation, therefore, in an excess of air. If, on the other hand, everything works correctly, in addition to the MAF sensor, thanks to some specific calculations performed internally, the ECU is able to precisely and accurately dose the amount of fuel. Let's roll up our sleeves and immediately take a look at the main formulas, so we can use them later with a practical example. Let's start with a very important formula that allows us to derive the load and thus understand how much work our engine is doing. It is good to specify that the values present in this formula do not come from the maps of the original file, but are already preset by the manufacturer during the development phase of the engine control unit, or from the measurements performed by the few sensors present in the system. Let's try to understand this formula better through its parameters. MAF is the measured value of the flow of the air mass entering the intake duct expressed in kilograms per second, but it is often expressed in grams per second in the maps contained in the original files. This is the volume represented by the displacement of the piston inside the cylinder expressed in cubic meters, but normally the technical documentation expresses it in cubic centimeters. This is the engine rotation speed in engine revolutions per second, starting with revolutions per minute. There would be a factor of 60 to take into account 60 seconds in 1 minute. This is the air density, which in standard conditions, 15 degrees Celsius, and 1,013.25 kilopascals of dry air equals 1,225 kilograms per cubic meters. So, the only parameter that could be indirectly limited by the ECU is the number of engine revolutions, depending on the limitation applied to the fuel injected. It is for this reason, on this type of file, that the fundamental maps to be modified to increase performance are the fuel quantity limiters. Moreover, as we have already seen, diesel engines always work in a condition of excess air, so the main parameter that the ECU must always calibrate appropriately remains the quantity of fuel to be injected for each cycle, so that excessive smoke is not produced in the fuel system and that the smoke limit thresholds are not reached. Precisely for this reason, two other formulas are useful. With the first, we obtain the total mass of air inlet, given the air fuel measured by the MAF sensor and the number of engine revolutions. Let's explain the components of this formula. We have the flow of the air mass measured by the mass airflow sensor and expressed in kilograms per second. The number of rotations of the crankshaft for each stroke, for a 4-stroke diesel. In this case, it's equal to 2. And the number of engine revolutions per second. With the second formula, however, we calculate the fuel to be injected to maintain a relatively high AFR value, thus avoiding smokiness. The calculation is possible by knowing the total mass of air inlet and the value of instantaneous AFR that the ECU commands. This part represents the mass of total incoming air. Instantaneous AFR is the air-to-fuel ratio to be used. Given that this strategy, based only on the engine load formula, is imprecise as it considers data of density, temperature, and standard air pressure, it is necessary to use a formula that calculates the density of the air, taking into account the pressure inside the intake manifold measured by a possible MAP sensor or calculated internally by the ECU, of the atmospheric pressure and temperature of the intake air. Let's take a look at this together. APS is the measured value of the atmospheric pressure from which the ECU is able to estimate the pressure present in the intake duct through mathematical functions and maps. This is the ideal gas constant, valid for clean air entering the intake manifold, whose value is 287.05 joules in degrees Kelvin per kilogram. This is the temperature of the air drawn into the intake duct. Let's try to simplify what we have talked about so far, taking some reference data to apply to the formulas seen. This is our example data. RPMs, 1,800. Airflow mass measured by the MAF sensor, 8,210 milligrams of incoming air. Ambient temperature, 20 degrees Celsius. Atmospheric pressure, 1,000 hectopascal. Engine displacement, 2,148 cubic centimeters. Absolute pressure in the intake manifold, 2.3 bars. Number of rotations of the crankshaft for each stroke, 2. First of all, we make the appropriate conversions of the known data to be able to correctly apply all the formulas examined above. First, we need to know the engine revolutions per second. Knowing that 1 RPM equals 0.0167 RPS, we calculate the revolutions per second performed by the crankshaft. We multiply the RPMs by their equivalent in RPS, resulting in 30 RPS. Now let's put this value aside, which we will need later on. Then we convert the air mass flow measured by the MAF sensor and expressed in milligrams of air per cycle to kilograms per hour. Let's start by finding how many milligrams of air enter the engine in a minute. Then divide the engine revolutions per minute by the number of rotations of the crankshaft for each complete cycle, stroke, and multiply the result by the air mass flow measured by the sensor MAF. We continue by converting the airflow into kilograms per second. Take the previously calculated MAF value and divide it by 1 million. Necessary to convert the values from milligrams to kilograms, and then by 60, value corresponding to the seconds that make up 1 minute. Let's continue our conversions by looking at the temperature and pressure data. To convert the degrees centigrade into degrees Kelvin, we just need to add the value 273.15 to the degrees Celsius. To convert the pressure bars into pascals, multiply the value 100,000 by the absolute pressure. We obtain the value 230,000 pascals. Finally, we convert the engine displacement from cubic centimeters to cubic meters. Now we finally have all the data converted to be able to apply our formulas correctly. Let's start with the calculation of the air density. Remember that the RA is the ideal gas constant, valid for clean air entering the intake manifold, and is 287.05 joules in degrees Kelvin per kilogram. And now, let's calculate the engine load, which defines how much work the engine is doing under the conditions described above. As we can see from the application of the formula, the load value exceeds 100% precisely because the engine is supercharged and therefore works with a volumetric efficiency greater than 100%. Thanks to the carburation maps contained within the original file, our ECU is now able to correctly calculate the mass of fuel to be injected, since it applies the air-fuel ratio formula in reverse. So, to derive the mass of fuel injected, we need to know the instantaneous air-fuel ratio, which we assume to be equal to 24, and the flow of the mass of air that we saw earlier as 8,210 milligrams of incoming air. We develop our formula and we find that the mass of fuel to be injected is equal to 342.08 milligrams of fuel injected. This result therefore indicates the total fuel to be injected to maintain an AFR equal to 24. And if we want to know how much fuel is injected into each cylinder, we simply divide the value found by the number of cylinders, which in our case corresponds to 4. So, the ECU is able to estimate, in addition to engine efficiency, the fuel to be injected into each cylinder, equal to 85.52 milligrams of fuel injected. Now, we analyze the critical point of this system. The measurement made by the MAF sensor must be as faithful as possible to reality, because any inaccuracy in measurement affects the prevention of smokiness and makes all the calculations seen so far inaccurate. In fact, if the measurement were affected by an error, the actual carburation in the exhaust could be fatter or leaner than expected, despite the fact that the fuel threshold value imposed by the smoke limiters is respected. For this reason, the MFM strategy was only used for a few years, until the early 2000s. So the few vehicles that you might find yourself modifying using this strategy are very dated, medium and large displacement engines, such as the Cummins. Subsequently, the strategy based on fuel calculation has increasingly taken hold, then arriving at the strategy featured in the following videos, torque calculation. In summary, in this video we have seen the operation of the MFM strategy in detail, analyzed the main sensor used, the MAF, and examined all the calculations that the ECU performs to always be able to work at maximum efficiency. In the next videos, we will analyze the latest generation strategy used by engine control unit manufacturers in detail, the internally performed torque calculation. That's all for today. See you at the next step.